All right, so the plan for today, the July 8th, Monday, July 8th, is really just to introduce the topic of vector calculus, vector analysis um, in chapter 16. So we're introducing the idea of vector fields, talking about what is a vector field, a couple different things related to vector fields. And then on Wednesday, we will start into line integrals and the fundamental theorem for line integrals. I was originally going to cover a little bit of line integrals today and then finish that up on Wednesday. But after I kind of review today's lecture, I don't really think we have enough time. I think that would just be too much to bite off for today's lecture. So I think we might have a little less than a full lecture today with just 16.1, but really not enough time left over to really get a reasonable start in 16.2. So I haven't quite, I kind of made that decision, you know, pretty much right before class. I was reviewing everything. So I haven't quite decided yet whether I plan to post maybe a supplement tomorrow with, say, an intro to 16.2 and then finish 16.2 and 16.3 on Wednesday, or whether I'm just going to knock those both out on Wednesday. So I'll kind of take a look at how I think Wednesday will look, and if that's too much material, now that I've pushed part of that back to Wednesday. But I definitely thought it was too much for today after I reviewed things. And then Green's Theorem 16.4 will be a supplement for this week. Okay, so starting into 16.1 vector fields. So definition, a vector field on R2 or Rn is a vector valued function of several variables f that assigns a two-dimensional or n-dimensional vector to each point xy or x1 through xn in the domain. So what does that mean? Well, it means, for instance, in a two-dimensional domain, we'll take this to be the domain of our function f. My inputs to f are points in the domain, like maybe this point, say, like 1, 1, and my output is a vector. So I have kind of an input space, and then I have an output space. But the output space is also two-dimensional, the same as the input space. So I could think of maybe this point in the input space getting mapped to maybe a vector like this in the output space, but we also know that we can kind of move vectors around. That's one of their main characteristics is they have a length and a magnitude, but not a specific position. So, this vector would be the same vector, or even this vector would be the same vector. So we could say that, this input maps to that output, a vector that looks like that over there, and maybe a different input, this red input, might map to an output that looks like this vector, which maybe we could write here, or we could write here, wherever we like, as long as it has the same direction and magnitude, it's the same vector. But since I can move my vectors around, I can actually kind of overlay my output space on top of my input space. In other words, I can say for this red point taken as an input, I can place the initial point of the vector at that point and then just draw the vector in this kind of input space over here. Or I could do that for the other input as well, the one that's up here, like at roughly 1, 1. I could say, well, I could take this vector that could be in the output space, but I could just overlay that on top of the input space, and I could say that this point 1, 1 gets associated with this vector that looks maybe something like that. So what's a vector field? Well, we can draw it graphically as a collection of points, a representation of points. Of course, we're not going to draw every point, but a selection, a representation of points along with their output vectors. So we pick some points to evaluate, We evaluate those points, figure out what their output vector is from this function, this vector function f, that will yield a vector, and then I attach that vector to that point, and I do that a bunch of times, and that makes a vector field. And of course, just like if I said I have an algebraic structure, say y equals x squared in basic algebra, I could make a tabular representation, and I pick some sample points. I don't pick every point. And in my graph, I would pick some sample points to get me an idea of what the graph looks like, and then maybe extrapolate from there and try to fill in with a curve or something like that. So a couple of notes, similar thing here is when we represent a vector field graphically, we tend to overlay the input and output spaces. So we take a sample of points that are input points. For each of those input points, we get an output vector, and we attach the initial point of that vector to that input point. And that gives us a graphical representation of a plane in this case, or maybe an n-dimensional object that has a whole bunch of vectors pointing in all different directions on it. A second note is there's a bit of a context issue here. Sometimes when we make a vector field, we scale all the vectors to the same length, when it's really the direction information that we're more interested in than the magnitude information. And sometimes this is not done. So sometimes, we keep the vectors lengths proportional to one another. Shorter vectors appear shorter and longer appear longer. But quite often, if you keep that proportional representation, the thing just ends up looking like a jumbled mess where there are too many vectors crossing over each other and so on. So often they're scaled down to get really the direction information and maybe lose some of the magnitude information, but at the benefit of being more readable. So, just like any pictorial representation, the goal is to present a lot of information in a quick and digestible way. And, that there are always going to be some trade-offs for better ease of use, maybe with the cost of loss of some information. So just a note on that. So if you see a vector field and all the vectors are the same length, that doesn't necessarily imply that the magnitude of f is actually the same everywhere. It might just be that it was scaled for demonstration purposes. Okay, so let's draw two examples of vector fields, and just, on your paper, draw a couple examples, draw two examples. It can be anything you want. Just, draw a vector field or two. I'll give you about 30 seconds. It shouldn't take long. And then I'll draw a couple, and we'll just kind of discuss a couple of things about it. So, pretty open-ended question here. Just, put some points down, draw some vectors attached to those points, and you've got a vector field. So take about 30 seconds or so. Okay, so tons and tons of vector fields we could draw. A couple maybe interesting ones, something like this. I'm actually going to draw this in red. I think it'll show up a little better. We could have something like this where we maybe have all of our vectors pointing towards the origin. And when our vectors are close to the origin, they're small in magnitude. A bit further away, maybe they get a larger magnitude, and further away still, an even larger magnitude. And I think you get the idea. I could fill in the other 6 little slices there with similar vectors to these 4 that I just most recently drew, but I think you get the idea here. I could also have something like this, maybe where kind of along the y direction, I'm going away from the origin. And kind of in the x direction, I'm going towards the origin. And then in my quadrants, I might have a behavior kind of like this. And kind of similarly down below. Maybe something like this. And of course, there's nothing special about the origin. I could have just as well, you know, drawn a vector field with everything going towards the point, whatever, 6, 7 or something, or, going towards 6, 7 in the x direction and away in the y direction, or, the origin is just kind of a convenient place to anchor things. Now, what does this vector field mean? Well, I mean, I suppose as simply a vector field, it doesn't really have a meaning. It's just an abstract representation of some mathematical idea. But I think the best way to think about a 2D vector field is to imagine water flow. So to imagine that at each point, maybe I am interested in this point. I put a little meter, I imagine a 2D surface of water. I put a little meter in there and it tells me which direction the water is flowing and how fast it's flowing. So I put my little meter in at this green point here and I see it's flowing down and to the right at a pretty fast flow rate. If I put a meter here, if I dip it in there instead, it's flowing down and to the left, but at a much slower rate of flow. If I put it up here on moderately high on the y-axis, it's flowing directly downwards at a moderate rate of flow. So I can imagine that's what each of these vectors represents, is direction of flow at that instantaneous point and rate of flow at that point. And I can also imagine that maybe if I dropped, say, a ping pong ball in here, in this water that's kind of flowing this way, in this case, it's kind of flowing in from the sides and then up and down as it gets towards the middle. I can imagine that this water is going to carry the ping pong ball along with it in some direction. It's going to, when it's near the initial point of this vector that I've drawn here, the ping pong ball is going to go more or less in the direction of that vector. But of course, as the ping pong ball starts in that direction, we haven't drawn all of the vectors. I mean, as soon as it moves away from that initial point, it's going to start following a slightly different vector, a slightly different direction, maybe a different flow rate as well. And so I just kind of interpolate between these different vectors. And I think that something like this, if I dropped my ping pong ball in here at like something like 9, 2 or something, it might take this path. It might kind of start working its way to the left and then eventually look like it's trying to join the y-axis here in the middle. Or if I imagine putting a ping pong ball here at, say, like -5, -1, I see this is going to get pushed horizontally much longer before the kind of vertical deviation starts to really pick up. So maybe something like that. So I could draw some of these, what are sometimes called flow lines or streamlines, just kind of imagining that I'm dropping like a ping pong ball into water and what's the general path it would take. And it turns out that under some reasonably lax conditions, these flow lines do not intersect one another. So we tend to, if we're drawing flow lines like this, to understand a vector field in a slightly different way. Instead of drawing the vectors, drawing these kind of flow lines in a sense, we would typically draw them as non-intersecting. And you could draw these on your pictures as well, of course. Whatever vector field you came up with, you could imagine putting a ping pong ball into water in a few different places, and what kind of path would it take that roughly follows the arrows that you drew. So I think that's the best way to kind of to visually interpret a 2D vector field like this. And for a 3D vector field, it's a little harder to envision, but you could think of, air currents that could be going left or right, forwards or backwards, or up or down, or any kind of combination of that. And if you put a little, grain of pollen or something like that in the air and let go of it, what kind of path would it take through three-dimensional space? That would be a way to think about 3D, but we'll see that, once you get a 3D picture and you start drawing a whole bunch of vectors on it, it's not very appealing to the eye. We can deal with like 3D surfaces and things pretty well, but a whole bunch of lines poking around in 3 dimensions is a bit hard to interpret. So maybe the graphical representation isn't quite as helpful in 3D as it is in 2D. And of course, once we get to 4D or higher, we're not really going to be drawing those. Okay, so let's look at this example then. We'll look at some specific vector fields, and let's try to match each of these functions with the graphical representation below. So here I have 4 graphical representations, and I have 4 functions. Let me shrink this just a tiny bit so I can fit it all on here. There we go. So I have 4 functions and 4 graphical representations. So f of xy equals y. I remember f is taking 2 variables as input. It's taking a point and R2 as input, and it's giving out a 2-component vector. So its I component, its first component is y. Its j component, its second component is 0. So the horizontal component is y, and the vertical component is always 0. Well, I can actually pick out right away which one of these this has to be, because the vertical component is always 0, and I see top left, top right, and bottom right, they all have non-zero vertical components, at least in some cases. So I could pick out right away that this has got to be A. Now, does that make sense? Does it, I mean, I've used process of elimination, but let me just double check. I mean, who knows, maybe there was a typo or something in the problem. Does it make sense that this vector field at the bottom left should be yi, or y comma 0? Well, what would this mean? Well, it's independent of x. So as I change x, things don't really change. But as I change y, when I have vectors that have their initial points that are higher up on the positive y-axis, my horizontal component gets larger positive. I should be pointing further to the right. It should be longer pointing to the right. And I do see that when I'm fairly high up on the y-axis, my vectors are independent of x, whether I have this vector up here or this vector here that's to the left or right. The magnitude, the direction don't change, but I'm pretty high up on the y-axis. That's a pretty long vector pointing to the right. When I'm lower on the positive y-axis, again, as I adjust the x-coordinate of the input, those vectors don't change, they're the same vector. I'm also small positive on y, so I have a small magnitude pointing to the right for my vector. And then similarly in the third and fourth quadrants, well, here y is negative, so I'd expect to have a vector pointing to the left. Its first component should be negative, second component 0, also independent of x, and similar analysis to above. I'm pretty confident that this bottom left vector field, this graphical representation, is indeed an accurate representation of f of xy equals yi. Another one that I can knock out pretty easily is part C. This is x times j. So it has 0 for its y component, or for its first component, for its I component. And it has x for its j component, its second component. So be a little bit careful here. X and y are, in a sense, playing two roles. They're playing the kind of scalar x and y roles as the inputs, the location of the anchor point for the vector. And x and y are also playing a kind of behind the scenes role as like the horizontal and vertical components, in a sense. We're trying to be careful to not call them the x and y components here, to not conflate things too much, but there's the horizontal and vertical component of the vector, the output, coming into play here as well. So I note here that for example C, the horizontal component is always 0, and of course that eliminates top left, top right, or bottom left. It's got to be bottom right by process of elimination. And again, does this make sense? This is very similar to part A. So as an exercise, go through and check a couple of examples, make sure that this geometric representation meshes with the algebraic structure. So check it in a similar way to how we checked part A. Now let's look at the other two, B and D. These are a little bit more complicated. I see I do have two components for each of them, and I have non-trivial things in each component. So for B, I have x as the first component and 3y as the second component. So what does this mean? Well, this means that when my anchor point has an x coordinate that is, say, farther to the right, that is more positive in the x direction, when that's where its anchor point is further to the right, it has a larger component, a larger first component, a larger horizontal component pointing to the right. So the further to the right the anchor point is, the more the vector should be pointing in the rightwards direction. And then just the opposite, the further to the left that it is, when x is negative, if I'm on the left half of the plane, if I'm towards the left side of the picture here, if that's where my anchor point is, x is large negative, my first component should be a large negative number, and my vector should be pointing significantly to the left. And then, of course, a very similar thing can be said for the y component. When we're on the top half of the plane, the higher up we are for the anchor point, the more vertical upwards our vector should be pointing. And on the negative half of the plane, when our initial point has a negative y value, that second component should be negative, and the further down we are on that initial point, the more that our vector should point downwards. So I think it's got to be this top left one, right? When I get higher up and closer, when I get closer to the middle horizontally and higher up, my vectors point more directly up in the vertical direction. When I get close to the middle horizontally and lower down, my vectors point down. And then just, very similarly in the x direction when the y values are small. That's consistent with all that I just said. If I were to look at the top right, I see that, sometimes when I have a large negative x here, for instance, and y is 0, in this case, I actually have a vector pointing directly upwards. It looks like no or 0 for the horizontal component and a large positive vertical component when x is negative and y is 0. And that doesn't mesh at all with part B here. But of course, that does mesh with part D. When y is 0 and x is negative, we just get a positive number times j. That's just a vector pointing directly upwards. So this looks like it should be D. And again, if we want to understand these vector fields in a slightly different way, we could imagine these points as being like ping pong balls that we're dropping in here. And, in the top left, these ping pong balls would just kind of get pushed away from the origin in this kind of manner. Part in the bottom left here, we would have our ping pong balls getting pushed sideways. The ping pong balls would be traveling slower as we work our way down towards the x-axis. And then once we cross over the x-axis, they start going the opposite direction, but just going sideways one direction or the other. And then vice versa with the bottom right here. These would just be moving in the vertical direction. And it kind of looks like on the top right, we actually have, looks like they would be moving in roughly loops or circles or something like that. So again, another way to kind of understand these vector fields, thinking of these as representing water flow and what happens if you put a ping pong ball in at one point, what path does it follow? Any questions to this point? I think one of the most difficult things with vector fields, just to kind of wrap your mind around, is the fact that we're kind of simultaneously looking at the input space and the output space on the same picture. And both the input and output spaces are two-dimensional. So I think that's the hardest thing to kind of get over. And once you get used to it, once you get acclimated to that, it's a little more straightforward. Okay, so now let's try to sketch the following vector fields. F of xy equals xi plus yj, or f is the vector with first component x and second component y. So maybe take a minute or so and try to plot maybe 5 or 6 different vectors in some different points on the plane to get an idea of what you think this looks like. Take about 60 seconds, and then we'll come back and we'll go through the answer here. Okay, so maybe just for this one, I'll make a small table of values over here. So I have some input points that I just kind of picked more or less at random, but just one from each quadrant. So for instance, the point 1, 1 sitting right here, that's an input point. What vector should I attach to that? Well, the vector associated with 1, 1, the point 1, 1, is the vector 1, 1. So I want to go over 1 and up 1, and that's my associated vector. Let me maybe actually make that, let's say, green. For negative 1, 2 as the input point, for this input point, what vector should I attach to that? Well, of course, that's the vector with horizontal component negative 1, vertical component 2. So I want to go 1 to the left, 2 up to get to my terminal point. For 3, negative 2, again, that's associated with a vector with components 3 and negative 2. This is a pretty simple problem to work out, right? So 3, negative 2, that's my input point, and the vector that's associated with that, I go over 3, down 2 to get to my terminal point. And then, of course, negative 5, negative 4, associated with the vector -5, -4. So this is my input point, and the vector that I want to associate with that is going 5 to the left and 4 down. So that brings me to what? -10, -8, like here. That's where I want my terminal point. And I think I have an idea now, just looking at these, the small sampling, roughly what the vector field looks like. So I'll just throw in a couple of extra vectors here. I know that when I'm close to the origin, my vector magnitudes are small. When I'm far away, they're large, because when x and y are both large in magnitude, then the magnitude of the vector is large. And I know they point away from the origin. So I have small vectors pointing away from the origin, near the origin. Moderate length vectors pointing away from the origin when I'm moderately far away from the origin. And I have never claimed to be a good artist, so this is just rough. And then long vectors pointing away from the origin when I'm far away from the origin. So something like this, right? Not a very pretty sketch, not perfect, but it gets us the idea that, if I take a ping pong ball and stick it here, it's going to go directly away from the origin, and it's going to actually speed up as it gets further away from the origin. Now, what would this vector field look like? F of xy equals xi plus yj, very similar to this one, but then divided by root x squared plus y squared. Well, this seems like it's qualitatively pretty similar to the last one. I mean, the direction information is the same. All that I've done is divide by the scalar root x squared plus y squared. All I've really done is change the magnitude of the vectors, not their directions. Their directions are the proportional relationship between the x and y here. I've changed the magnitudes. In fact, what I've done is I've scaled the magnitudes of these vectors all to be length 1. So the vectors very near the origin get stretched a little bit. The vectors way out here are still pointing directly away from the origin, but they're scaled to be length 1. So we actually get basically the same picture we had above, but just all our vectors are the same length. And so on. I only have one more quadrant to do. I'll just fill it in really quickly. Okay. So going from A to B, if we imagine that this was our vector field we were interested in, we could plot this vector field instead, where I divide each vector by its length and then plot that. That gives me a bit of a cleaner picture, especially if I was asking a computer to do this and I was getting a lot of these that were kind of, well, none of them are going to overlap in this example, but suppose that, a different example I had for these longer vectors, if they were, overlapping all over the place like this, that's going to turn into a jumbled mess really quickly. It wouldn't happen here because they all happen to be all going radially out. But you can see how in another example, we might be getting a jumbled mess like this. But if we scale everything down to the same magnitude, I might be able to see a little better what's going on. I might be able to get something like this without things kind of just crossing over everything if the magnitudes are getting unwieldy. So I could always take my vector function, divide it by its length to get a bunch of unit vectors, and then plot that instead. If I was using an online plotter or something like that, that might give me a nicer picture. And it's not going to change the direction information. It will change the magnitude information. So I lose that information of, so to speak, how fast my ping pong ball is moving at each location. But maybe it makes the whole thing a little more digestible, a little easier to interpret. Okay, and then our third example down here, example C, here I'm going to do a little bit of work first. So for example C down here, I see that my function f is horizontal component y squared, vertical component is x squared. So I noticed that the horizontal component depends only on y. If I draw it kind of off to the side here, when y is 0, there's 0 contribution horizontally. When y is 1, there's a small positive horizontal contribution. 2, it's a little bigger. 3, it's even bigger still, and so on. And when I go negative, I get a similar result because of the square. For my vertical component, what does it look like? Well, it only depends on x. So nicely enough, I can kind of do a similar thing with x and my vertical component. When x is 0, I have no vertical component. Well, I don't have no, but the vertical component is 0. I have no vertical movement in my fluid flow. Then I have a little bit when I deviate a little bit from 0, a little more when I deviate a bit more, and even more still when I deviate even more. So I see, at the origin here, I don't have any flow. If I put a ping pong ball there, it just kind of stays there. If I go up and to the right, I have flow that's a bit up and a bit to the right. If I go up and to the right further, I have flow that's more up and to the right. And it almost feels like I'm setting myself up to draw something like a previous picture, but I have to be a little careful. If I go, up quite a bit, but only a little bit to the right, I have a little bit of an upward influence, but a large rightward influence, right? Or if I go way to the right and only up a little bit, I have a little bit of a rightward influence and a large upward influence. Down and to the left is interesting as well. When I'm way off to the left and way down, I have about balancing influences, but they're quite large. And then smaller as I get towards the origin on this, like roughly on this 45-degree line. But if I go a bit to the left and quite a bit down, well, a bit to the left and quite a bit down, I'm moving a lot to the right and a little bit up. A bit to the left and not quite so far down is not quite so much of an influence to the right. Or quite a bit to the left and just a bit down, I'm moving mostly up. And if I draw my flow lines, I get something that kind of goes right along this 45-degree line here. And then I get things like this. I get kind of pushed away from the origin and then pulled back in. So in my mind, I think in an example like this, I would have to either draw a ton of arrows, or once I kind of see what's going on, I think it's actually an easier graphical representation to interpret to draw the flow lines and fewer arrows, because it makes it kind of more clear what's going on. That's at least to my eye anyway. But you can use these flow lines along with the arrows to to help the visualization. Any questions on that? All right, let's look at an example here, and this is going to be more of an algebraic example, although it's motivated by geometry. Let's show that each vector in this particular vector field, f of xy equals yi minus xj, is tangent to the circle centered at the origin with radius r equals root x squared plus y squared. What does this picture look like? So again, f is y comma negative x. Its horizontal component is y, and its vertical component is negative x. So let's make it easy for ourselves to start with. When x is 0, we have no vertical component, only horizontal. When x is 0, we have a horizontal component y. So when y is a little bit positive, we're pointing a little bit to the right. When y is a bit more positive, we're pointing more to the right. And when y is quite positive, we're pointing quite far to the right. And then just the opposite when y is negative. When y is a little bit negative, we're pointing a little bit to the left. Moderately negative, pointing moderately to the left. And quite a bit negative, we're pointing quite a bit to the left. What about when y is 0? So on the x-axis, well, when y is 0, we have 0 comma negative x. So when x is negative, when my anchor points, my initial points are to the left on the x-axis, I have vectors that have 0 horizontal deviation that do have a vertical deviation, but when x is negative, they're going to point up, and when x is positive, they're going to point down. When x is a little negative, they point a little bit up. Moderately negative, they point moderately up, and then quite a bit negative, they point quite a bit up. They have quite a nice magnitude in that upward direction. And then vice versa, when x is positive, our second component's negative, these point down. What about intermediate values? What if I have like x is 1, y is 1, or something like that? So it's something like 1, 1. The vector that's going to attach to 1, 1, like over here, is going to look like 1 for its first component, this 1 going there, and then negative 1 for its second component. So it's going to go to the right and down. And then if I get further away from the origin, the size of x and y get larger when I get further away from the origin. So the length of my vector gets longer. And I see that I have this kind of swirling pattern. And I think I can kind of imagine that if I dropped a ping pong ball in here, that it would kind of make its way maybe around a circle. Maybe these vectors in this vector field are all tangent to circles of whatever radius is needed to match their initial point. So that's the geometry motivation here. If I have a point x comma y, there's a vector going from the origin to that point. And then I also have a vector coming from the vector field that's the output when that point is input. Well, if I want to be tangent to the circle, I'd be tangent to the circle if I'm perpendicular to the radial line, going from the origin to the point of interest, to the input point. So in other words, if I look at, what color haven't I used? Blue. If I look at this vector here, this is the vector with x component x and y component y, or first component x and second component y. And this vector over here is the vector big F, or with first component y, second component negative x. Well, these are perpendicular if and only if their dot product is 0. And their dot product gives me xy minus xy is indeed 0. So whatever xy I pick, when I draw the vector associated with that point from the vector field, and I consider the vector going from the origin to that point, that vector, when I kind of trace it, or when I swing it around radially 2 pi radians, that traces out a circle. And I do see that I'm perpendicular between those two vectors. Well, my vector field is tangent to all of those circles. And so this does kind of confirm my suspicion also that my little ping pong ball, if I drop it in here, will just kind of keep going around in a nice closed loop, which is in fact a circle. Any questions to this point? Okay, so let's look at a couple of 3D vector fields. We're certainly not going to try to draw these because they're messy enough to interpret when looking at the computer graphics. But we will try to match some of these. We'll try to match up a couple of vector fields to their these 3D plots. So let's consider the vector field f of x, y, z, 3 dimensions now, is xi plus yj plus 3k. So f's first component is x, its x component is x, its y component is y, and its z component is 3. The first thing I note about this vector field is whatever point x, y, z I'm interested in, the z component is always positive 3. It's the vectors are always pointing up no matter where I pick my anchor point to be. So if I see examples like these down here, where sometimes vectors are pointing down, where sometimes vectors are pointing downwards, I know that these can't be geometric representations of this vector field. Now, I suppose either of these I haven't excluded yet from being candidates on the basis of just this z component always being positive. My z component is constant, so maybe it would benefit me to look at, say, a 2D slice, which I could also think of a vector as a vector field and say 2 dimensions, x and y. So just doing this is kind of some scratch work over here. Since my z component is always just 3, I can look at what is my x and y contribution to that vector. When x and y are small positive, I get a vector pointing out like this. When they're moderate or large positive, I get a larger magnitude vector pointing away from the origin. We've done this one already. This was the xi plus yj one. We get something that looks like this. Now, if I imagine laying that flat and then taking each of these vectors and pulling them upwards, pulling their terminal point upwards 3 units, well, then I can see I'm going to get vectors that point away from the z-axis and are going upwards. Well, if I imagine my z-axis being somewhere, well, these vectors in the top right here all seem to be kind of pointing in the same direction. Sometimes they'd be pointing towards the z-axis and sometimes away from the z-axis. But it seems like over here, they're always seem to be pointing away from the z-axis, right? I mean, I can see just looking at vectors kind of at the edges over here, these seem to always be pointing more or less in the same direction, kind of up and to the right, where these are sometimes pointing up and to the left or up and to the right, or what looks like more kind of straight toward us, pointing away from that like middle axis of symmetry, you know, coming through here. So at this point, I'm pretty confident that top left is the correct graphical representation of this vector field. Now, again, I mean, you would have to be a heck of a good artist and extremely patient to be able to draw something like this by hand. Even interpreting this as the output of from a computer graphics program is not easy. So, most of the time we kind of restrict ourselves to 2D when we're interested in graphing or drawing anything. But there's nothing theoretically wrong with trying to graph it in 3D. Okay, and then let's look at example 5. So here we have our vector function yk, or in other words, 0, 0, y. I note that the x and or the horizontal contributions, both in the x and y directions, are 0. My vector should only point straight up or straight down. And I see whether they point up or down and what their magnitude is dependent on y, not x. So large positive y's give a vector that is pointing up and is quite long. Small positive y's for the anchor point, for the initial point, gives me vectors that are pointing up but are short. Small negative y's for the anchor point give me vectors pointing down but are short. Large negative y's for the anchor point give me long vectors pointing down. Okay, well, these ones on the bottom left here point down regardless of whether y is positive or negative. That can't be the right one. These ones point up regardless of whether y is positive or negative. That can't be correct either. These top two do switch direction. They go positive in some cases for y and negative in other cases for y. So let's be careful. We have yk, in other words, when y is positive, like over here, my arrows should be pointing up. And when y is negative, they should be pointing down. So clearly this is not the correct one, and this is. This might be about the only one that's simple enough that you might be able to draw this by hand and get a passable representation. We also note that when y is close to 0, the sizes of the vectors are fairly small, and when y is farther away from 0, the sizes are a bit larger. Okay, any questions to this point? So a little note here, I was actually going to write this up and discuss it, but the book actually does a fantastic job with these two examples, so I didn't think I had anything that I could add, and I figured, half of you probably have read this already, but just pointing out examples 4 and 5 in the book. In my copy, that's pages 1071 and 1072. There are two examples, one on Newton's law of gravitation and one on Coulomb's law. I think they're excellent examples, particularly the Newton's law and gravitation. Very nice examples of vector fields. So I would definitely recommend taking a look at that. I was trying to think of a way that I could put my own spin on it or something, but I think the book just does an excellent job with those examples. So I just wanted to point those out and make sure that you all see them, just in case you hadn't seen them yet in the book. But I would strongly recommend, going through those examples and trying to understand them. If you don't understand all the physics, that's okay. But, again, this really shows how a lot of this ties into physics. And one little note on the examples, particularly on Newton's law of gravitation, they go through and kind of show two different algebraic representations, one with everything written as vectors and another with everything written in terms of the scalar components. And you can see how when you write everything out in terms of the scalar components, it's this big, long, nasty equation. When you use some vectors and use, length of a vector and some vector operations, everything just collapses to a very nice, elegant little couple formulas. And that's often the case when you're dealing with things in 3 dimensions or even higher dimensions. If you try to split everything out, it often becomes pretty messy. But you know, one of the nice things about this notation, it is a bit esoteric. It is a bit cumbersome to wade through notation or to get used to it. But one of the nice things is you can write a lot of, especially repetitive things, very concisely and in a nice form. And it often ends up being in a form that you recognize from a similar problem in lower dimensions, from a similar like scalar type problem. You might see parallels between the vector formulation and the scalar formulation when you write everything out nicely in terms of vectors. Okay, so then moving on to example 6. This is an example from the book. So this is, I think it was examples or exercises 35 and 36 from the end of 6.1, I think, if I remember right. So I just pulled this straight out of the book, the wording and everything. So the flow lines, or sometimes called the streamlines of a vector field, are the paths followed by a particle. We kind of talked about this already. So we see that the vectors in a given vector field are tangent to the flow lines. So first, let's take a look at the vector field xi minus yj. And let's just get a rough sketch of this vector field, get an idea what it looks like. So maybe I'll actually push part C down just a little bit. Okay, so my vector function has first component x and second component negative y. So when y is 0, when I'm on the x-axis, I'm just looking at things like x comma 0. When I'm on the positive part of the x-axis, I'm moving horizontally to the right. When I'm on the negative part of the x-axis, I'm moving horizontally to the left. So this is for y equals 0. For x equals 0, what do I have? 0 comma negative y. So here, when I'm on the positive y-axis, I'm pointing down. And when I'm on the negative y-axis, I'm actually pointing up. And my intermediate input points look something like this. And I can probably guess what some flow lines are going to look like. Maybe something like this, something like this, and like that. As kind of an aside, we're going to take a look at differential equations here. We're going to interpret this in terms of differential equations. And if you, depending on what you covered in Calc 2, I typically don't cover it in my differential equations section in Calc 2, but you might have, or if you've taken a differential equations course before, you might have heard of the idea of phase portraits or phase planes or phase space or something like that. You might have even heard of that idea in engineering or physics or something. And this is closely related, what was really, I suppose, in this context, exactly related to that idea. So that phase portrait is just kind of a representation of a vector field. So just a little side note there, tying it into something you might have seen before. Again, if you didn't see it before, certainly not an expectation for this course, but some folks in this course might have heard of that before. So I think my solutions, my kind of paths that a particle might take, look something like these red lines, depending, of course, on where I start my particle, where I place my ping pong ball in that water that's flowing like this. Now, I do understand that when my ping pong ball is local to one of these arrows, it's going to flow basically in the direction of that arrow. It's going to flow tangent to that arrow. Or in other words, this these vectors are going to be tangent to these red curves that represent the path of the particle, or some potential paths of particles. So in other words, the instantaneous rate of change of the x coordinate with respect to time is going to look like the x coordinate, the horizontal coordinate of my vector field, but that's just x for this particular case. And the instantaneous rate of change of the y position of the particle as it's moving along is going to look like the y, or the vertical component of my vector field. Well, that's just negative y. So I have a couple of differential equations. The x dt equals x, the y dt equals negative y. I'm not really interested in knowing something about time. I want to know what these paths look like, these red paths. I want to know an algebraic representation of these red paths. So really what I want to do is eliminate the parameter t, get a differential equation in x and y, and then solve for a function, say y equals f of x, something like that. Well, I know that dy dt over dx dt, just from parametric equations, is dy dx. And I know that that is, well, dy dt is negative y, and dx dt is just x. I just have a first order separable differential equation, or I have 1 over y dy equals negative 1 over x dx. I can integrate both sides, and I get log y equals negative log x plus, and I'll just call this c tilde. I'm calling it c tilde because we're going to want to make another constant c in just a minute here. So I see that I have that y is, well, negative log of x is log of x to the minus 1, or log of 1 over x. So that's 1 over x. And then this plus c tilde, that can become a log of c and come all inside of the same log. And this just gives me c over x. So something like y equals 1 over x might give me these two red curves, and something like y equals negative 1 over x gives me those two red curves. No, I'm told that I want the equation of the flow line passing through 1, 1. So if I draw my ping pong ball at point 1, 1, say here, what path does it take? Well, here I'm saying I want y to be 1 when x is 1, or 1 equals c over 1, says that c equals 1. So the path my particle or ping pong ball will follow is y equals 1 over x. Let's repeat this for this example down here. So again, I'll draw out a vector field. I'll kind of sketch some possible solution curves, use differential equations to generate an algebraic representation of the solution, and see if my intuition matches the algebra. So I see that my horizontal component is always 1, and my vertical component is x. So when x is 0, I just have a horizontal component of 1. It's the only thing that contributes. When x is a little bit positive, I'm going a little to the right and a little up. When x is more positive, I'm going a little bit to the right and more up. So I have a steeper line. When x is a little bit negative, I'm going a little to the right and a little bit down. When x is a bit more negative, I'm going a little to the right and more down, so steeper down. And I think some solution curves will look something like this. Maybe something like a parabola. So here I see that the x dt, the instantaneous rate of change in the horizontal position with respect to time is the horizontal component of f, it's just 1. The instantaneous rate of change in the vertical position of my little particle or little ping pong ball is the vertical component of f, it's x. And of course, dy dx is dy dt divided by dx dt, or just x. Well, dy dx is x. This is, I mean, you could hardly even call it a differential equation. 1/2 x squared plus c. Quadratics just as we expect. And if we want to ask the question, which one of these curves, which one of this family of curves goes through 1, 1, 1 equals 1/2 plus c. C is 1/2. And I see y is 1/2 times x squared plus 1. So it looks like maybe something like this curve here. Okay, any questions so far? Okay, and then introducing one last little topic. We will talk a little bit more about this in future sections, but just introducing it here. The idea of gradient fields. So if we have a function little f of xy that's a scalar function of 2 variables, it takes 2 variables as input and gives a number as output. And if we consider its gradient, grad f, first component partial of f with respect to x, second component with respect to y, we could think of this vector here as a function that takes 2 inputs, a point x comma y, and yields 2 outputs, fx at xy and fy at xy. It yields an output that's a 2-dimensional vector. It takes a point in R2 as an input and yields a 2-dimensional vector as an output. That sounds an awful lot like a vector field, right? This is just the vector field in R2, and we give it the name, we call it the gradient vector field. So really what we're saying is that if we imagine little f of xy representing some kind of, or let's say z equals little f of xy representing some surface in 3 dimensions, maybe like a hill, we're saying at each point, our vector field, our vector that's output, tells us the direction to go in if we want to, if we started walking in that direction, if we want the direction of greatest increase. And of course, 3 or more variables completely analogous. So let's just compute the gradient vector fields for these 2 functions. So my function defining the vector field is just grad f. Its first component is partial of little f with respect to x. That's just 2x. Its second component, partial with respect to y, is just, well, 2 times 1/2 y. So just 2x comma y. Or it more or less looks like that vector field where all of the vectors are pointing away from the origin. But the 2x means that, the vector is going to be a little more horizontal than they are vertical. But It's basically like that. Basically looks more or less like this one here. And for a three-dimensional example, well, the first component is the partial of little f with respect to x, so that's just y. The second component, partial with respect to y, is x plus z squared. And the third component, partial with respect to z, is 2yz. And I'm not going to make any attempt to draw that. I will do a terrible job, but you could, maybe try to use an online direction field or vector field plotter, and it might be able to give you a three-dimensional representation that you could make heads or tails of, but this isn't something that we could reasonably draw by hand. And then last, this idea of a conservative vector field. We say that a vector field F is called a conservative vector field. If you've heard of things like conservation of energy, like conservative forces, that's all tied into this idea. It's a conservative vector field if there exists a function little f such that big F equals grad little f. And if so, then we call little f the potential function. So I know that if I have a little f given to me, as long as it's differentiable, I can come up with a vector field related to it called the gradient vector field. But the question here is, if I'm given a vector field, it might or it might not be the gradient vector field of some function little f. Sometimes it is, sometimes it's not. If it does turn out that that vector field that I'm given is indeed a gradient vector field, if it's the gradient of some function little f, then we call it a conservative vector field, and we call little f the potential function. If big F, if this vector field turns out to not be the gradient of any function little f, if there's no such little f that satisfies that, well, not a big deal. It's just not a conservative vector field. It's still a vector field. We can still do stuff with it, but it's just not a conservative vector field. So example 8 is f of xy equals 2x comma y, a conservative vector field. And we haven't talked about how to test a given field to see whether it is, but here we can clearly see yes. And of course, the reason is we just computed that this field is the gradient vector field of this function. This vector field is grad f, where little f is x squared plus 1/2 y squared. And an interesting question is this vector field, where it's the constant vector field, where at each point, x comma y comma z in three-dimensional space, we have exactly the same vector, ABC. Is this a conservative vector field? And this one I'm actually going to leave as an exercise. So give it a little bit of thought, think through it for next time, and when we come back next time, we'll address this, and then we'll move on in sections 2 and 3 with line integrals. So that finishes our lecture for today. So again, my tentative plan is to cover sections 2 and 3 on Wednesday. But again, I kind of mentioned I caught an audible at the last minute here because I didn't think this is about where I expected to be, and I didn't think in the last 15 minutes I could really actually start line integrals in any meaningful way. So I decided to push that to Wednesday. So either post an extra supplement sometime on line integrals, or if I feel we can actually get through the material for both on Wednesday, we'll just keep them both on Wednesday. But if I do change anything, and if I'm going to post the supplement on 16.2 or 16.3 tomorrow, I'll let you know. Otherwise, we'll just convene on Wednesday and pick up right where we left off. All right, that wraps us up for today. I will see you all on Wednesday.